How large is 1 TB of data? Is it possible to search 1 trillion records in seconds? When evaluating a data warehouse product or technology, a common question arises: how much data can this product handle? Many vendors often answer that their products can process data at PB or even ZB scale. This creates a perception that a good product should at least be able to process hundreds of TB, whereas 1 TB or a few hundred GB of data is too little. It's often considered a small scale that is negligible. Is that really the case? Let's first examine how large 1 TB of data is from a business perspective. Databases primarily handle structured data, among which the largest space consumer is the ever-growing transaction data, such as bank transaction records, telecom call logs, supermarket sales records, tax payment records. Each record of this type occupies little space, typically requiring only a few dozen to 100 bytes when stored efficiently. For example, a bank transaction record only needs the account number, date, and amount, while a telecom call record only needs the phone number, date, and duration. Let's take bank transaction records as an example. The data table typically looks like this. If we assume each record is 100 bytes, or 0.1 kilobytes, then how many such records can fit into 1 TB of space? About 10 billion. To generate 1 TB of data in a year, it requires about 27 million transactions per day, roughly 300 per second. This transaction volume is certainly possible for large and medium-sized banks with hundreds of millions of customers, but for small and medium-sized banks with millions of customers, it could take several years or even more than a decade. And that's just 1 TB. If we're talking about a few hundred TB, even large banks would struggle to accumulate that much in a year. Just saying how many TB of data doesn't give you a real sense of scale. You only get a real sense of what it means when you convert it to daily transaction numbers. Some non-top-tier organizations do have data volumes reaching hundreds of TB or even PB. How does this happen? Among these organizations, some use media data, such as images, audio, and video, which occupy significant space. For example, just 1 hour of video can take up about 6 GB, making it easy to accumulate 1 PB of media data. However, such unstructured data is usually not stored in databases for computational purposes. In addition, some organizations accumulate data over many years, adding 50 GB one year, 200 GB the next, along with intermediate calculation results that weren't cleaned up promptly. This makes it easy to accumulate hundreds of TB or even PB of data. Although this data may be stored in databases, it's seldom used simultaneously in a single computation task. The remaining organizations collect data automatically from devices or gather behavioral data from a large user base, generating tens of millions of records daily. Over a year, this can amount to hundreds of TB or even PB. While this data does need to be stored in databases, it's seldom used beyond basic retrieval and extraction operations. From a business perspective, 1 TB is a substantial amount of data. But what about from a technical perspective? To process data, a database needs to read it at least once. Even with an SSD that can read 300 MB per second, note that vendor-advertised speeds are unattainable in real-world operating systems. Merely reading 1 TB of data without any computations would take approximately 3,000 seconds, nearly an hour. So, how is it possible to process 1 TB of data in seconds? It is simple: use 1,000 hard drives. In theory, this setup could read 1 TB of data in around 3 seconds. But that's just in theory. In reality, factors such as non-sequential disk reads, network latency, write-back operations for sorting and association calculations, and concurrent second-level query demands must be considered. As a result, it's normal to be several times slower than that theoretical speed. In fact, we've all experienced that it takes a considerable amount of time to copy 1 GB file from the internet. If you need to move 1 TB of data, the fastest method might be physically transporting the hard disk. This gives you a tangible sense of how large 1 TB really is. Therefore, from a technical perspective, 1 TB of data also means hours of processing time or thousands of hard drives. It's a significant amount, let alone hundreds of TB or even PB scale data. From both a business and technical perspective, 1 TB is a significant amount of data. In fact, single data analysis tasks rarely involve TB scale data, and PB scale data is almost impossible. For most users and their computational tasks, the data volume typically ranges from tens to hundreds of GB. Distributed databases usually utilize only a few to a dozen nodes for a certain task. Therefore, most users should focus on whether a data warehouse product excels at handling small data under 1 TB, as this is the most common scenario. Since many big data products are designed to handle hundreds of TB or even PB scale data, they should be fine for processing small data, right? Not necessarily. Processing such large data scales often requires massive clusters. Small data, however, rarely requires a cluster, and even when it does, the cluster is usually very small. Many mechanisms developed to tackle big data challenges actually hinder performance when applied to small data computations. For example, the automated management and task allocation mechanisms of large clusters limit programmers' ability to freely assign tasks and distribute data to each node, wasting each node's efficiency. Additionally, large clusters, with their many nodes, are more prone to errors, requiring robust fault-tolerance capabilities. However, these capabilities are unnecessary for single machines or small clusters but have to be employed. Moreover, the complexity of these frameworks themselves can lead to excessive consumption of limited resources. However, it seems that most big data products in the industry boast PB or even ZB scale data processing capabilities. Does this imply that no products are specifically designed for small data? In fact, there are. For example, ISPROC SPL focuses primarily on optimizing performance for data scale ranging from hundreds of GB to 1 TB, achieving single machine performance comparable to clustered systems in many cases. This lightweight product itself consumes very few hardware resources, avoiding the issue of complex big data products failing to fully utilize resources for business calculations. In addition to focusing on the data volume of big data products, should we also consider the performance metrics claimed by vendors? For example, can we trust the searching a trillion records in seconds claims made by many vendors? As previously estimated that 1 TB holds roughly 10 billion rows, and looping through it once takes several hours. For trillions of rows, which can amount to tens or hundreds of TB, is achieving search speeds in seconds realistic? Actually, this isn't always the case. Searching in seconds doesn't necessarily require a full traversal. If searching by a unique identifier, such as a phone number, the amount of computation after building an index is not very large. An index essentially stores IDs in order along with their corresponding positions in the original table. This enables binary search to quickly locate the target ID, thereby finding its position in the original table. For example, in an index with ordered IDs, finding the record with ID 82 using traversal search would require sequentially checking each record. It would only find the record with ID 82 after checking up to the 9th record. In the worst case, it requires up to n comparisons, where n is the total number of IDs. Binary search, however, leverages the ordered IDs, eliminating the need to search from the first record. Instead, it starts by checking the middle record, which has an ID of 25. Since 25 is smaller than 82, all records before 25 can be ignored, as they definitely do not meet the condition. The search continues in the remaining half, effectively splitting the index into two. Since binary search eliminates half the data each time, it requires at most log base 2 of n comparisons to find the target. The computational complexity of this point search task is logarithmic. When the total data volume is 1 million rows, the number of comparisons required is approximately 20. Even if the data volume increases to 1 trillion rows, the number of comparisons only rises to 40, just doubling. Modern computers can perform 40 search operations in less than a second. Therefore, almost all databases can achieve searching a trillion records in seconds. This is not surprising and hardly worth boasting about. Searching a trillion records in seconds is a task involving massive data volumes, yet it can be completed quickly. In reality, the opposite scenario is also common. Seemingly small data volumes can require extremely time-consuming computations. Many tasks involve less than 1 TB of data, Yet distributed databases with multiple node cluster often take several hours to complete. For example, a celestial body clustering task involves relatively small data volumes, 11 tables with 500,000 rows each, totaling less than 10 GB. However, a distributed database used 100 CPUs and took 3.8 hours to complete the computation. What could explain this inefficiency? Because the complexity of this operation is quadratic, the computation is extremely intensive. The celestial body clustering task involves 11 celestial body pictures, each containing 500,000 celestial bodies. Some bodies may be duplicates across different pictures. The data of each picture is structured into a data table of 500,000 records, with each record containing the coordinates and attributes of a celestial body. The specific computational task is to use one picture as the base, and for each celestial body in it, identifying duplicates from other pictures whose coordinates are sufficiently close, then merging them to produce a refined picture with clearer coordinates and more accurate information. During computation, the process begins by taking the first celestial body from the base picture and comparing it with all 500,000 celestial bodies in another pictures. This requires 500,000 comparisons to identify all duplicate bodies. Next, this comparison is repeated for all 500,000 celestial bodies in the base picture, which completes the comparison between the two pictures. This results in a total of 500,000 times 500,000 is equal to 250 billion comparisons. Finally, the base picture is compared with the remaining 9 pictures, leading to a total of 500,000 times 500,000 times 10 is equal to 2.5 trillion comparisons. A distributed database using this quadratic algorithm has no choice but to perform the brute force computation of 2.5 trillion comparisons. Completing this in 3.8 hours is already a decent result. A point search on trillion-scale data requires only 40 comparison operations as long as a good algorithm is adopted. However, clustering of celestial bodies on 10 GB of data requires 2.5 trillion comparison operations if a quadratic algorithm is employed. Therefore, computational performance isn't directly related to data scale, but primarily depends on the amount of computation required by the algorithm. The most important feature of a good big data product lies in its ability to implement efficient algorithms and achieve higher performance with less computation. However, the vast majority of these big data products on the market are SQL-based systems, and they perform quite poorly in this regard. Let's take celestial body clustering as an example again. Actually, far more efficient algorithms exist for this scenario, but are difficult to implement in SQL-based systems. Such algorithms operate as follows. First, sort the celestial bodies in the other pictures by their coordinates. Next, use binary search to identify the two bodies nearest the distance boundary for each base celestial body, which narrows the comparison range down to around 1,000 records. Finally, compare each record in this smaller range, which dramatically reduces the number of computations, with the total computation being approximately 500,000 times log base 2 of 500,000 times 10 times 2. With one factor of the multiplication becoming logarithmic, the computational load is reduced by nearly 500 times compared to a quadratic algorithm. However, SQL-based systems lack support for high-performance algorithms like ordered computation and non-equijoin optimization, making it impossible to implement such low-complexity methods and forcing them to resort to quadratic-level calculations. While writing UDFs is an option, the substantial effort required significantly diminishes the value of using such databases for computations. In fact, by stepping outside SQL-based systems, a solution becomes possible. For example, SPL supports ordered storage, efficient associations, and other features enabling easy implementation of the aforementioned algorithms. By employing this logarithmic then multiplicative approach, SPL completed the celestial body clustering task in just 2 minutes on a 4-core laptop. This simplified the distributed environment to a single machine, significantly lowering operation and maintenance costs. Of course, other technologies like Python, Java, and C++ could be considered. However, Python does not natively support binary search, and using third-party libraries requires integration with pandas, which makes implementation cumbersome. Moreover, Python's multithreading doesn't support true parallel computing since it uses fake multithreading. While workarounds are possible in practice, they are complex and expensive to implement. Although high-level languages like Java and C++ could theoretically implement efficient algorithms for celestial body clustering, their high programming complexity and development costs make them impractical. In comparison, SPL provides a richer function library and a visual programming interface, making it easier to implement high-performance algorithms. In summary, the scale of structured data processed in data analysis tasks is not very large in most scenarios. What we truly need is a technology capable of effectively handling data sizes from tens of GB to around 1 TB. In practice, many scenarios involve small data volumes but require intensive computations, such as various complex intertable joins and common object event calculations. The performance of data analysis tasks is determined not by data volume but by computational workload. The key to reducing the workload is a good algorithm. Without a good algorithm, you have to use brute force methods, and even processing 10 GB of data on a cluster can take n hours. Conversely, an efficient, low-complexity algorithm can search 1 TB of data in seconds, even on a single machine. When selecting a data warehouse technology, you should understand the scale of data involved in your computational tasks and don't overemphasize big data, and you should focus on the technology's algorithmic capabilities rather than the data volume it claims to handle. Only in this way can you find the right product.